Hello everyone, welcome to the third edition of our Carbon Smackdown series. My name is Jeff Miller and I'm Head of Public Affairs. Today's topic is wind, something that seems like such an easy answer to so many of our energy problems, but as our speakers, lab scientists Glen and Ryan Weiser will show us, the wind option is a lot more complicated than we think. It's still hopeful, but a lot more complicated. So we're going to start with Glen. Please welcome him.
Okay. Thanks, Jeff. Okay, I want to talk about today a project that we started way back in the early 2000s to build a vertical axis wind turbine. So those of you who have a bit of rebel in you, you might be interested in this topic. It's a project that's jointly with Empire Magnetics of Roanoke Park, and they're working on the Alternator for it, and the State Rocket Center in Mias, Russia. This is a program funded by the Department of Energy. Initially to employ Russian scientists who were in their weapons program. And the State Rocket Center is it has the assets of NASA, basically, and they build the submarine-launched ballistic missiles for Russia. And so we had 100 or so guys from over there working at various times with different engineering expertise. If you want to reach me, there's my name and email number. And the company in Russia is the State Rocket Center Vertical now that's been formed to commercialize the technology in Russia. So just so you know right away what we're talking about, this is shot in Russia near the South Ural State University. That's what the turbine looks like deployed there. This isn't a particularly good wind site, but there's an educational institution next door. And there's a very nice monument to Kurchatov, the father of the Russian atomic bomb. Let's go back. Let's go back and take a moment to just reinforce the impacts of climate change. And this one, of course, is close to home. This is the meter or so that many believe is built into the system already. And what we see is that this meter sea level rise that's likely coming, likely coming is going to flood Central Valley up to Walnut Grove or so. And this will probably occur during some massive spring storm that'll start the melt and runoff and take out the levees. But we have a tremendous amount of infrastructure work to do if we're going to protect a lot of the low-lying Bay Area areas. And so it's urgent that we start moving on. Now, in the last interglacial, there was a 6-meter sea level rise, and here is Florida, with a sea level rise forecast at about 5 meters in 100 to 200 years. And as you can see, you can imagine the infrastructure projects that would be necessary to actually protect the massive population centers that are down there. And they're basically out of reach, I think. I think, these are infrastructure projects that will never, they'll maybe start, they'll do some, but by and large, people are going to have to migrate in order to do this. And so this means doing everything we can, as Berkeley Lab is right now. Just a reminder, this is total sea ice. I kind of keep track of what's going on the Arctic sea ice levels. And as you can see, this is accounting for the thickness of the ice. It's a model from the University of Washington that's published on the National Snow and Ice Data Center. You can see we're right here in this sort of could be a very catastrophic loss of sea ice right now. And that just accelerates the process. So we need to do everything we can. So let me go back and talk about this project, which started as a non-proliferation program project in '93. It was one of several US government projects at the time that was with the former Soviet Union. And there are many that are ongoing. And Thomas Turok, who's in the audience, I believe, I saw Thomas a moment ago, is the manager of the program now. I was the manager a while back. And if you're interested in working in some of the former Soviet Union countries, you might chat with him. We used the lab connections to industry and to the newly independent state scientists to build these coalitions. And then we required the US industrial partner to match the program dollars. And so this effort was about $2 million of DOE money and about $2 million effort from our industrial partner over 6 years, and about 70% of the DOE money went to the Russian scientists. We designed this unit for the urban environment. We designed it for low noise and ease of manufacturing. And the ease of manufacturing, I think, will be important perhaps in developing world applications, because we'd like to actually transfer most of the manufacturing into those locations so that they have an economic basis for developing these wind turbines. 5 units came here in December to Berkeley. And now we're testing this under the Technology Commercialization Fund program, which Cheryl Fragilakis' department manages. And we're really pleased to have those resources. Thank you, Cheryl. Let's see, next slide. Okay, just a reminder for those of us who love the distributed grids ideas that electricity goes both ways, and the cheapest grid is the one you don't have to build. And when we start thinking about plugging in our electric vehicles, we're going to wonder, where's this extra energy coming from? Vertical axis turbines are a possibility. They're good for small wind, we believe. They're two-dimensional airfoils. Here's one right here. This is a turbine from the unit, turbine blade from the unit. And it is, you can see a two-dimensional form, relatively easy to work up in a fiberglass shop, and can be manufactured with modest technology. The airfoils are supportable at both ends, so you can get some strength, and we're also in the vertical mode able to use a large diameter alternator and get to higher voltages and use less wire. And the vertical machines should be good in gusty low wind conditions, which are those that you expect in an urban environment and with lower towers. And in addition, the blade speeds are lower, so we have a lower noise unit, and the impact with any object that's flying in the air is also lower. Let me put this in context of our familiar Human Development Index graph here that I think was just shown by Ashok a while back. And here's the annual energy output of the unit we're talking about today. It's just right about at the knee of the Human Development Index in terms of per capita. So it'll produce, along with a solar cell, most of the energy typical household should be able to need. This is the design point with relation to other wind turbines out there. This is the theoretical curve of the maximum energy you can get out of the wind. Here's the efficiency, 0.4, 0.5, 0.6. And down here is the tip speed ratio. This is how fast the blade is going through the air relative to the wind speed. And most modern turbines operate up here around 50%, the big horizontal machines that Ryan will be talking about later on. So they're very efficient units, but they run at tip speed ratios of 7 or so. So in a 25 to 30 mile an hour wind, the tips are moving in 200 to 300 mile an hour range, depending on the unit. And we designed down here to be at about 2.5 times wind and get efficiencies about 35 to 40%, and we believe we're there, actually. The project started off with scientists modeling different blades. In Russia, here's the stainless steel blades that were built up for test in the hydro facility that I'll show in a moment. This is the helicopter factory in Kumurtau in Bashkortostan in Russia that is building up some of the first test prototype units. And of course, all the blades were designed using most of the modern engineering techniques to look for stresses and failure rates. This is the kind of facilities we had available for us. This is about 100 feet high right here. This is a water tube right here that goes around, and here's a huge propeller. They open up a dam and turn on the power and start turning this guy and start a water flow. They get a very pure water flow through here, and then they put the blades inside that tunnel. As you can see right here, here's one of the mounted blades, and they're able to put a fair number of diagnostics around this, and then they scale from water flow to airflow to get what the behavior is in air. And we learned a great deal about the absolute correct airfoil to use in the project using this. And it was also tested in wind tunnels. The unit itself starts at about 2 to 3 meters a second in a 4-degree angle of attack. Here's the shape of the profile. And Empire Magnetics has developed a pancake alternator right here, permanent magnet alternator that sits in the unit. And by and large, there's one moving part, which is the rotor, because the alternator is attached to the rotor. Here is the first Alpha unit that was built. This was in Russia. This is the shake stations for the submarine launched ballistic missiles for the Soviet Union, and they did the shake testing there on the unit. And here's the computed power curve showing that we kick in at about 3 meters a second with about 100 watts and achieve about 3.4 kilowatts. at 11, 12 meters a second. I'm sorry, what's that?
The curve turns over, but there's no data.
Oh, this right here? Oh, you're talking about this. This is computed, okay? And so what actually we do is past here we break the unit because there's so little wind that it's not worth withstanding the dynamic forces. And so what we do is just shut the unit down, okay? That's part of the control strategy for the unit. Yeah, and these data points we have to reproduce now here in the United States. Just to give you an idea of the energy output, we're talking about being designed by and large for class 2 wind, which is like coastal California and ridgeline California. We're talking about 4,350 kilowatt hours per year and about $1,000 worth of energy at 24 cents a kilowatt hour. But now I'm paying 47 cents a kilowatt hour when my daughters come home and leave on the flat irons because the rates are that high. And so I think we're actually competing, to take energy off the top and competing at very high energy rates. And anywhere in the world where people are running diesel generators, for example, to bring in their power, they're paying about 50 cents a kilowatt hour. So that's really the competition in terms of economics. There's two versions of the unit. One that has these rings right here for structural stability on top and bottom, like the one you saw in the picture. And this one right here, which has struts. And we're going to go with this unit configuration for some structural resonance reasons that you'll see in a moment. We also, under the program, built a 30 kilowatt unit. And this is sitting in a steel factory in Chelyabinsk, Russia. And has been erected over the winter, and I think they just got a few turns out of it the other day. But basically, the Russians are out of money, and I don't know what's going to happen to the 30 kilowatt unit right now. One of the major problems that comes up in the course of doing vertical axis wind turbines is the structural resonance, and this is an exaggerated highly exaggerated visualization of the modes. This mode right here, and these lead to fatigues that limit the lifetime of the unit. And what we want is very high lifetimes and to kind of avoid these resonance modes. And so this is a mode right here that is interactive with the tower. And this is a mode that's almost purely it's with the tower a little bit, but it's almost purely a blade mode. And so these are the computed displacements versus frequency. So we wanted to verify those here in California. And one of the reasons that we also went to the second unit design is to raise this mode out of the operating range of the turbine. And we've done that. So this one right here, that's mode 1. Okay, this is down in Fresno at Toshgen Towers. It's being driven by an eccentric right now just to get the structural quantities right. And so that's the mode that you saw that would be the tower interaction mode, and that's relatively easy to fix. And then the next mode is the wobbling back and forth mode, and we'd like to just avoid that because we don't want to fatigue the blades as much. We want to minimize the fatigue load on the blade. And there she goes, right there, right there. And so you can see the oscillations going. Now, this has all been computed and designed to withstand this over the lifetime of the turbine. However, we'd like to avoid this mode totally, and we will. Okay, and this is the unit running at 145 RPM. You might just notice that the blade kind of disappears against the sky when it's going that fast. So this is totally balanced now and in full speed mode. And that's about the speed that it runs at when it's generating its maximum power. So we're going to start a test program under the Small Wind Certification Council standards adopted by OEA in January. This standard applies to turbines that are less than 200 square meters in swept area. And the SWCC is going to be an independent certifier, and they're going to provide a placard that goes on the unit on all small wind turbines that go through their test program. And the unit will placard, sort of like a Consumer Reports, it'll placard the power of the unit at 11 meters per second wind, the annual energy output, assuming a 5 meter per second Rayleigh distribution for the wind, and that's what you saw calculated earlier for this unit at about 4,300 or so. The sound level, which is the less than 5% threshold at 60 meters, this was an item that I think is in the favor of horizontal wind machines because they're considerably noisier, particularly when they're changing direction. And one of the reasons they're not widespread in urban environments. And then the cut-in wind speed for the production of power. Then we'll do a 2,500-hour endurance test, and 25 of those hours will have to be greater than 15 meters a second. And this standard generally uses the IEC standards with some relaxations. They're not quite as stringent as the big turbines are. And this is likely to be used by the states for rebates. Several states are already saying they're going to use this to determine whether rebates will be given. So our first place that we're going to install, which will be at the end of the month or the very beginning of August, is in the Sassoon Bay, a really nice windy location at the Marine Reserve. You know where the mothball fleet is out there? And this is a National Oceanic and Atmospheric Administration buoy. One of these has been put aside for us, and this tower will come off and the turbine will go up on top of there, and it'll be sitting out here in very clean wind and relatively low altitude. And we have another site in the Bay Area, and we've been working with the city of San Francisco on that. And that'll probably get installed sometimes in August. Okay, so I'm going to end with a little bit of the market work that Ryan did actually at the very beginning of this project. He worked with Global Energy Concepts and outline what the market was for these units. And in 2004 or so, I think this was data from the American Wind Energy Association, grid-connected homes of 15 million units potential. This is where there's wind and where there are people. Okay, so the U.S. market potential for has grown 78% in 08. So the growth rate for small wind is right now staggering, okay? And we expect that it'll stay that way. And if this kind of growth rate, 80% to 100% growth rate continues, then perhaps a WIA's goal will be met, which is 1/3 of this potential of this 16 million wheels, which is 50,000 megawatts by 2020. And it would have to grow at this rate to make 2020, by the way, which is 3% of domestic electricity demand. Now, we want 20% renewables, or wind, and Ryan's going to talk about the other 17% in a minute with a bigger chunk. But this is still a reasonable chunk if we can get the penetration of small wind to this level. So we're on track right now to 1,700 megawatts by 2013. And anyhow, if this is all realized, this would be sales of about $1 billion and 10,000 people employed. So in the work that Ryan did, he also outlined where we had to be price-wise. This is the knee of the photovoltaic history. In other words, the number of units shipped versus the price of the unit. And as soon as they got down to around $4 a watt, it took off. And now we're way off this curve, I imagine, a long, long way. But this was where we were shooting for with regard to installed costs. There are barriers to the overall growth of small wind, particularly in urban areas, mostly prohibitive zoning regulations and height restrictions. But California just passed a law guaranteeing that if you have 1 acre, you can put up, I believe it's an 80-foot tower. And if you have 5 acres, you can put up a 100-foot tower. And this is guaranteed right that you have. The San Francisco Urban Wind Task Force met over the last couple of years, and San Francisco has streamlined the permitting process for wind to the same as solar. And they continue to maintain an interest in developing urban wind in San Francisco, and we're happy to be working with them on that. Another issue is low resolution resource assessments. In other words, finding out exactly what the wind is likely to be at your house so you can make a decision about the economics. And there's few off-the-shelf inverters for grid tie right now. There's some, but we need massive manufacturing volumes in order to get the prices down. And low manufacturing volumes are always keeping prices high. And then this is particularly suitable for developing countries, and there's a lack of capital in the developing countries. But these problems, I think, are all fixable with investment and political will. And so we're hoping that we will get to a point where small wind is a viable market for folks. Okay. So we take questions after Ryan's talk? Yeah, okay, great. Ryan, you're on.
Well, good afternoon all. It's a pleasure to be here. In my 20 minutes, I'm going to really shift gears rather dramatically to discuss the current status of the wind market and the future prospects of the wind market, but focusing not on the smaller scale turbines that Glen described, but rather much larger utility scale turbines that currently represent the bulk of the aggregate wind power market. It's important to recognize that these turbines are much more sizable, not only than the smaller turbines that Glen's describing, but also than many of the turbines that perhaps many of you are familiar with from the Altamont Pass. These are turbines that now typically stand on towers of about 80 meters in height, and they have wingspans of around 80 meters in height as well on average. So think of effectively pretty close to a football field of wingspan and almost a football field's worth of hub height as well. These are absolutely massive machines. So for the purpose of this presentation, I'm going to cover two, sort of three topics. The first one, a quick description of the current status of the US wind power market in these utility scale applications. I'll then talk about some analysis that we did now a couple of years ago that have analyzed the prospects of achieving much higher levels of wind penetration, 20% by 2030. In the US wind market. And then I'll conclude with just a single slide that describes some of the market and policy needs that might be essential to overcome or to meet in order to achieve higher levels of wind penetration. Most of this presentation is based on two reports. One over here on the left will be coming out in a couple of weeks. The other one on the right, done or completed a couple of years ago. If you want more information, I can certainly pass on at least this one now, this one in a couple of weeks. So starting with current status of the wind power market, that market has, as you can see on this graphic, seen a very significant growth over the last decade or so. About 10 gigawatts of wind were installed in the US in the year 2009. That represents roughly $21 billion of investment and resulted in an aggregate wind power capacity at the end of last year of about 31 gigawatts. That put the US in the lead globally in terms of cumulative installed wind power capacity. Again, 35 gigawatts, as you can see here. China in second place, a couple European countries after that. The US also, until last year, for about 4 years running, the US led in annual capacity installations as well. But last year we were surpassed by China. This year we will be probably doubled by China. At the very least. But the US certainly is in strong position to remain in that second spot globally for many years to come. In addition, you can't really see the legend here for whatever reason. The important point here is that wind now represents a significant fraction of the newly installed wind power capacity in the United States. Of all the new electric power capacity added in the US in the year, this is 2009, just trust me, 39% of it was wind. In 2008, well, you can't see the label here either, 44% of the capacity added in the US was wind, 35% in 07, 18, 06, 12, 2, et cetera, et cetera. So compared to natural gas, which is the blue portion of these bars, wind is the second largest source of new electric capacity additions for a number of years running, and now represents a very sizable fraction of the new capacity coming online in the US. And so it's no longer really to call this an alternative power source in some sense. If anything, maybe we can call coal an alternative power source. Wind has beaten coal for many years running in terms of new capacity additions in the US. Coal is this brown area. In terms of the geographic spread of the market, a pretty significant geographic spread, the exception being the southeastern US where there is effectively no wind or very little on land or onshore wind at least. But you can see significant capacity additions in the middle part of the country, the wind belt of the US, but also pretty significant capacity along the Pacific coast states as well as portions of the Northeast as well. All of these projects to date have been located on land. However, there are a number of projects being planned, or at least proposed, offshore in the US. There are 13 projects that are in more advanced stages of development, most of them in the Northeast, the Great Lakes area. we sort of expect to see at least some of these units being constructed over the next several years, though the economics of offshore wind are not currently nearly as attractive as for onshore wind. So what's driving the growth? Well, pretty simple, economics and policy. On the economics front, wind does, in most locations, not everywhere, but most locations, wind is the lowest cost renewable option that is available. In addition to that, for much of the 2000s, wind was pretty darn competitive with new natural gas and coal power stations. And so the economic positioning of wind, both relative to other renewables and relative to some of the conventional energy sources, the fossil energy sources, is pretty good. In addition to that, wind certainly benefits from a number of favorable federal policies and state policies, federal tax incentives, a variety of Recovery Act programs that were initiated last year, state renewable energy programs and policies of various forms, and perhaps in the future, state, regional, and federal carbon policies as well.